This video looks at elastic versus inelastic collisions. First of all, what is an elastic collision? An elastic collision is when kinetic energy is conserved. And an inelastic collision is when kinetic energy is not conserved. It's really important to note that energy will always be conserved, but it might change form. And in the case of elastic collisions, no kinetic energy is transformed, all of that kinetic energy is maintained. For inelastic, you have not lost, but you've, you can talk about it like that. You've lost some kinetic energy because it's transformed into another form, with maybe gravitational potential energy, as in the example I'm going to show you. Now, a quick way to remember the difference between elastic and inelastic. This one works for me. I think of a rubber band, and when you stretch it, it returns to its shape, and that's behaving as something elastic should. So elastic means you've conserved that rubber band and it works when you stretch it. But for inelastic, if you let's change colour so we're getting our memory working using different colours. That's how our brain tends to work. So for inelastic, if you stretch and snap, then that elasticity is no longer working as it should. So it's become inelastic. Okay, it's still stretchy and the model breaks down there, but you get the idea. So that works for me to remember. Now an example to try and cement this in a little bit more. The importance of it, I guess, is some collisions, obviously the energy is not conserved, and we can come up with some unusual results if we assume that energy is conserved. So here's this example here. We've got a, just change my pen, we've got a rifle, and it's being, it's a rough looking rifle, you get the idea though, and it's being fired. So a bullet is coming out of the rifle, very aerodynamic looking bullet there, and it's hitting a sandbag which is attached to the ceiling somewhere, and when that bullet hits the sandbag swings up through a particular vertical height. Now, this was a system that they used to measure the muzzle velocity of the bullet. Now you can do it with high-speed cameras and such, but originally this is what they would have done. And the reason this works is because the kinetic energy, the gravitational potential energy gained as it shifts upwards through that particular height should be the same as the kinetic energy that's been transferred to the sandbag, and that should be in theory the same as the kinetic energy that the bullet had. Okay, it's really important with your notation to have subscripts that are descriptive, so you know what's going on and don't get confused. Now, what we're going to do is calculate some values for the velocity of the bullet. Let's just draw these in arrows. So we've got the gravitational potential energy gained by the bag should be the same as the kinetic energy gained by the bag at that point, which should be the same as the kinetic energy from the bullet. And from the kinetic energy of the bullet, half mv squared, we can calculate the velocity of the bullet. So the bullet weighs 30 grams, the bag weighs 10 kilograms, and the height that it moves through in this case is 7.2 centimeters. Okay, these are not arbitrary values, they give us a nice result when we do this correctly. So let's just proceed. With the gravitational potential energy, step 1, we've got mgh, gives us that gravitational potential energy. The mass is 10 times by g, which is also 10 newtons per kilogram, or meters per second squared, times the height is 0.072. Now why did I do that? It's because 7.2 centimeters is not SI units, but we're trying to follow SI units all the way through. And that'll give us 7.2 joules of energy. Okay, and that's unrounded as well, so we can put that same value into our next calculation. That 7.2 joules should be the kinetic energy gained by the bag. So 7.2, and that equals half mv squared. From this we should be able to calculate, well, in fact, if that's the kinetic energy gained by the bag, that's also the kinetic energy gained, lost by the bullet, if we're assuming an elastic collision. So we can go straight into this section here, which is finding the kinetic energy of the bullet. So the mass of the bullet, well, let's rearrange this first. So we're looking for V. We'll just start off with V squared because it's a multi-step calculation. I don't want to skip any steps and make it tricky to see. So we've got the half on that side, so we're going to multiply by 2, by 7.2. And then we've got the mass, which we're trying to get rid of, so we'll divide by the mass. And let's just write that out in full. 2 times 7.2 divided by the mass, which is 30 grams, is 0.030 kilograms. Mass is one of the exceptions when you're talking about SI units, because you've got that modifier K for kilo, kilograms. You would think grams by themselves would be the SI unit, but it's not the case. I'm not sure why. I haven't looked into that deeply yet, but that does work in this case. Now we have to square root everything, so we should see a V will equal the square root of 2 times 7.2 divided by 0.030, and I'll just quickly plug that into my calculator, and that equals 22 meters per second. Okay, but remember what we're calculating here, that's the muzzle velocity of the bullet, and that doesn't seem right, because 22 meters per second, that's roughly 20 meters covered in 1 second. That means it takes 5 seconds to go the length of a rugby field. Okay, that is way too slow for a bullet. So our initial, this is where our inelastic and elastic comes in. Our initial assumption right up here that the kinetic energy is conserved is wrong. No, it's not conserved. So what do we do? Well, there's another way that we can work this backwards, and that is to look at momentum, because momentum is always conserved, even if kinetic energy is not. So what we would do then, we'd introduce an extra step into this, where we take we still go from the potential energy of the bag to the kinetic energy of the bag, but then we go from the kinetic energy of the bag to the momentum of the bag. And then we take the momentum of the bag, and that is the same as the momentum of the bullet. And from the momentum of the bullet we can take the velocity, because momentum is mass times velocity. So this is a slightly different pathway. Even though kinetic energy is not conserved, momentum is. So let's just progress through that and see if we come up with what we're expecting. So if you remember, we had 7.2 joules was the gravitational potential energy. That's still the same, and that's still the kinetic energy of the bag. Okay, so we can use that to calculate the momentum of the bag. We know the mass. We can take the velocity from the kinetic energy and substitute that in here. So we'll just quickly do that part. From EK equals half mv squared. We know that V will equal 2 times EK divided by 2, divided by mass. Write that really carefully. Very easy to make mistakes and then the square root of all of that. Okay, I am rushing through this just a little bit because the video is beginning to extend too long, and that gives us 1.2 meters per second. So the momentum of the bag will then be 10 times 1.2 is 12 kilogram meters per second. That's a tricky one. So that is also the momentum of the bullet. So P bullet equals 12 kilogram meters per second, which is the mass of the bullet times the velocity of the bullet. So we can rearrange this to find the velocity. Let's see if we get something more reasonable. It should be 12 over 0.030, and we can already see this is going to work out well. Quick calculation, 400 meters per second, and that is much more reasonable. That means it covers the length of 4 rugby fields in 1 second, and that's in keeping with what we would understand the pace of a bullet to be. So again, just very quickly recapping, we had elastic collisions where kinetic energy is conserved, inelastic collisions where kinetic energy is not conserved. In this example of a rifle firing a bullet into a bag, we can work backwards from the gravitational potential energy to the kinetic energy to the momentum to find the muzzle velocity of the bullet. We can't do that using kinetic energy because kinetic energy is not conserved. It's an inelastic collision.